please hit subscribe.
This problem appears at the qualifying examinations for applicants for Japanese government or MEXT scholarships 2020. This problem is from the 2020 physics questionnaire for the undergraduate scholarships. The answer key and original questions are linked in the description. Now continue with problem 3. This is the second half. And again, the problem goes, as shown in figure 3, object A of mass m is moving with speed v on a frictionless surface. Object B of mass 3m is at rest and attached to the end of a spring with spring constant k. The other end of the spring is fixed to a wall. Objects A, B, and the spring are aligned in a straight line. After the collision, the spring is compressed. At time t equals capital T, the spring takes the maximum compression L. Now we need to find L, capital T, and the compression of the spring at time t equals capital T over 2. Now let's try to recall a few things that will help us solve the problem. First is the conservation of energy. So at every point in the process, before or after the collision, energy is conserved, and that means that the sum of the kinetic energy and the potential energy before the collision, for example, is the same as the sum of the kinetic energy and the potential energy after the collision. Another is the idea of potential energy stored in an ideal spring. And we know that from physics, and that is just 1/2 kx squared. Here k is the spring constant, and x is the displacement from the equilibrium position. So in our case, the equilibrium position is the initial position. That is when the spring is neither compressed nor stretched. So that is the initial position of our spring at the beginning of the problem. We also make use of the idea of simple harmonic motion in a spring. And just to recap, this is the differential equation that describes the motion of a spring in simple harmonic motion. On this side is the force due to the spring. So this is from Hooke's law. It is just the negative of the spring constant times the displacement from the equilibrium position of the spring. And on this side, it's just the mass times the acceleration. And we know that the solution to this is actually the sinusoidal function with a constant here. And in fact, if we try to get the acceleration given this displacement, so we just differentiate this twice. So we get this term here. And if we differentiate this twice, we see that that derivative is actually a times this angular frequency here, square of that, times sine of omega t. And then we notice that this term a times sine omega t, that's just this here. So we can replace that with x of t. And so we are left with omega squared times x of t. So the acceleration, if the object is in simple harmonic motion, the acceleration is equal to the square of the angular frequency times the displacement from equilibrium position. Again, we're just reminded that A here is the maximum displacement, so it's the maximum compression or stretching. Omega is the angular frequency, and m is the mass of the object. So here we just wrote down what we learned from the previous slide. And then for problem 3, we are asked for the formula for L, which is the maximum compression of the spring. Now, let's think about what happens at the maximum compression and what holds during that. So we know that, for example, the conservation of energy holds because the conservation of energy will hold any time at any point. And so even during maximum compression, this relationship holds. And also, during maximum compression, for example, here, if the spring is at maximum compression, it is about to come back, right? Because if it keeps moving forward, then it was not at maximum compression, right? So if it's at maximum compression, it would have to return to equilibrium position. And so at the point where it is maximum, where the compression is maximum, it is stationary. Its speed is zero. And so we can use this conservation of energy to solve for how long this compression is. So let's use the conservation of energy. And we know that the energy, the kinetic energy, is just 1/2 times the mass times the square of the speed of the spring, and potential energy of the spring is given here. So let's write them down. So here, this is the potential, or rather, this is the kinetic energy of object B at rest. So here, when it is at the initial position, here at equilibrium, it is moving. When this object collides with this, it starts moving at the speed of 1/2 v. We know this 1/2 v from problem 3.2. So this is from the previous video. And 3m is the mass of the object here. And 1/2, well, that's for the kinetic energy. 1/2 times mass times the square of the speed. And then at equilibrium, meaning at the initial state, when the spring is neither compressed nor stretched, the potential energy is zero because x here is zero. Remember, x is the displacement from the equilibrium position. So if it's at equilibrium, then x is zero, and so we have a potential energy of zero. So this is the initial state right after the collision. Now, at the state of maximum compression, we said that the object actually stops for a moment, and so the speed is zero, and the kinetic energy is therefore zero, but the potential energy due to the spring is maximum. So it is 1/2 times the spring constant K and times the displacement from the original position, or rather the equilibrium position, and that displacement is just L because L is the maximum compression, and we're talking about that time now. And so we have L squared here. And now we just solve this equation for L, and for example, we can cancel the 1/2 here, the 1/2 here. This 1/2, we have a square term here, so that becomes 1/4 times 3. That's why we have 3/4. And then the m remains, and then this v is squared, so v squared. And on the other side, we have L squared and k. And we just move the k down, and now we get the square root. And of course, this gives us our L. And therefore, from the choices, this is the answer. And we also note that this is the A here in our equation for the harmonic motion, simple harmonic motion. Question 4, we need to look for capital T, and that is, again, the time when the maximum compression happens. And we will use these equations here, these relationships here, to find capital T. So again, we say that capital T is when the maximum compression happens. And we know that because this is the relationship between the compression and the time, we know that when this is maximum, sine is maximum. That's because A here is a constant. So we need to find T such that sine of omega t is maximum. And what is the maximum value of sine? That's 1, right? And so we're looking for the value of capital T such that sine of omega t is 1. And that happens when the value inside here is pi over 2. So omega t equals pi over 2. Now, we can just move the omega here down here, so in the denominator, and now we have t. And now we just need to find the value for that omega. So again, we use this equation here. So we will just replace the k here with a given k, m here with a given mass, 3m. And if we do that, we get this relationship. So again, the k is just the k, x is just the x, m is 3m here, and this acceleration here, we take it from here, which is equal to negative omega squared x here. So the negative and the negative here cancel, the x and the x here cancel, and so to isolate omega, we just move the 3m here at the denominator, and now we get the square root. So we get omega equals k over 3m. And if we want t, because omega here must be in the denominator here, we flip the numerator and the denominator. So we get t equals pi over 2 square root of 3m over k. And that is this in the choices. Now we need to find the compression of the spring at capital T over 2. And this is not very hard if we already know the constant A here and the omega T over 2. So all we need to do is replace the T's with T over 2. And so let's do that. So here we replace that. X of T over 2 equals L sine of omega T over 2. So we just replace the T with this T here. And here L is equal to A. We already know this from question 3. So we are just going to use it here. And now, the nice thing is we also know what omega T is, right? That is from question 4. So from question 3-4, we know that omega T is pi over 2. And therefore, omega T over 2 is pi over 4. And so we can replace this whole thing here with pi over 4. So it becomes like this. We know that sine pi over 4 is actually 1 over square root of 2. And so that becomes L times this is 1 over square root of 2. And that is just this letter F in the choices. If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!